Hey there. So today's video is going to be a combination of the Putnam series and the PDE series, and the Putnam series we are going to be looking at the 2010 A3. So the question is on your screen right now. So as you can tell, the main focus of the question is this partial differential equation, except instead of 0 you have h of xy over here. But before we look at that partial differential equation, we'll look at this one, because this one is easier to solve and it also fits in with our purpose of learning the method of characteristics. For solving this partial differential equation, there are two methods. So the first method is that we convert this partial differential equation into this one. So if you remember, in the previous PDE series video, we had already solved this one. So if you can convert this equation into this equation, then the solution is pretty much in front of you. But I'm going to leave that method to you, and today's method is going to be a generalization of the geometrical method which we used to solve this one. So what we are going to do is we are going to notice that this has a certain geometrical interpretation, and that is the directional derivative. So if we take the gradient vector of f of xy and we dot it with the vector AB, then we get this exact expression. So this must be equal to 0. So well, what does this equation tell us? We have looked at this before. If the dot product of two vectors is 0, that means they must be perpendicular. And if a certain vector is perpendicular to the gradient vector of a function, what does that mean? Well, that means that the function doesn't change at all along this vector, which means that if we find a line, so let's say our vector AB is this. So this is the vector AB. So if we find a line which lies along this vector or which is parallel to this vector, so let's say this line, so these two are parallel. So this equation tells us that if we move from this point to this point on this line, the function does not change. Basically that means that this is a contour of the function, or you can say that the function does not change along this line. And what that means is that if we find the line along this vector and then we parameterize it, then the function does not change with the parametric variable. So firstly, the equation of this line is going to be bx minus ay is equal to some constant s, and now we'll try to parameterize this line. So how do we parameterize it? Let's say bx is equal to t, so that means that t minus ay is equal to s, so y is equal to t minus s by a. So now we can say that any point on this line is of the form t by b and t minus s by a, because this t by b is x and t minus s by a is y. So that means that if we change t, so now if we take f of this vector, because ultimately f is a function on R square, which means it's a function which takes in a vector and spits out a number. So if we take f of this vector, then the partial derivative along t is equal to 0, because as I said, if we move along this line, then the function does not change. But now it's really easy to solve this, because if we integrate both sides with respect to t, then this side will just cancel out the partial differential operator, and well, what is the integral of 0 dt? C. Except we are in the multivariable world, so this can in fact be any function of s. So this must be a function of s, because any function of s partial differentiated with respect to t gives us 0. So now this is a function of s. So well, we can say that f of xy, because this is x, this is y, is equal to c of s. Well, what is s? S is this, bx minus ay. So f of xy is equal to a single variable function of bx minus ay, and that is the general solution that you would have gotten if you had used the previous method which I alluded to. And now we'll move on to solving the Putnam question. But for that we need to solve this partial differential equation except with h of xy on this side. So how do we do that? Well, if you notice, the entire procedure will remain the same just with replacing 0 with h of xy, and the only time it will actually make a difference is over here. So over here, instead of having integral of 0 dt, we'll have integral of f of xy dt. And of course that is not something which we can evaluate because we don't even know what f is. That's what we had to find. So what we'll do is we'll use the simple trick which we always use for separable differential equations, because if you notice, this is just a separable differential equation. If I remove all this stuff, then what we end up with is a separable differential equation. So the only difference is that now it's a multivariable function, but since we are only differentiating it with respect to one variable, we can treat it as a single variable function. So over here as well, we'll replace xy with this vector for consistency. It doesn't really matter. And now what we'll do is we'll divide both sides by this thing and we'll multiply both sides by dt. So this is equal to dt and divided by f of blah blah blah. And now we can integrate both sides, because if we integrate these two, then this is just ln of f of xy, and that is equal to t. And then if you notice, we also need to add a constant function or a single variable function of s, because we are integrating with respect to t, and any function of s when partial differentiated with respect to t will give us 0. So ultimately this is what we end up with, and now we can just plug in what t and s are. So t was bx and s was bx minus ay. And now we are really close to solving the question, because we have pretty much solved for f of xy. We just need to raise both sides to the e. So we'll get f of xy is equal to e to the bx into e to some constant function of bx minus ay. But notice that f of xy equal to 0 is also a solution to this partial differential equation, but we didn't somehow get that solution, because if you see properly, then this can never be equal to 0. So we are completely missing out on f of xy is equal to 0. So where did we go wrong? Well, if f of xy is equal to 0, we can't really take ln, can we? So when we take ln, we have to specifically list that this or f of xy is equal to 0. So this kind of mistake happens all the time. We miss out something because we divided by 0, or we took ln of 0 in this case. So we just completely forget about one solution. So this completely misses out on the 0 solution. And of course you can argue that if you let this function equal minus infinity, then this becomes 0, then f of xy is 0. So we didn't actually miss that solution, but do you really count that as a rigorous argument, setting a function equal to minus infinity? So anyway, these are the solutions. And now the question says that if mod f of xy is less than or equal to some constant m, then we must prove that f of xy is identically 0, meaning that it is 0 no matter what value of x and y you put. So well, if this is the solution, then of course we have already proven the thing which we want to show in the question. But if this is the solution, can this ever be bounded by a constant m? So the answer obviously is no, because if it was yes, then the question would be wrong. So the answer is no, but we need to prove that it's no. So to prove that, let's say that we are varying y so that ay is equal to bx plus some constant. So I'll not use c because we have already used that. What can we use? Let's say k. And from there we can say that e to the bx times e to the c of k, which is obviously just a constant, let's call it k naught. So e to the bx times e to k naught is less than or equal to m. And if we take this to the other side, then we get e to the bx is less than or equal to m e to the minus k naught for all x. And that is of course false, because we can always choose a value of x to make e to the bx as large as we want, irrespective of what b is. So that means that we have proved that for this condition to hold, this must always be the solution and this can never be the solution, and hence we have solved the problem. Thanks for watching.